Generators make alternating current, as we've noticed, automatically. You can adapt them to make direct current, but they naturally make alternating current as the coil changes. Now, what is alternating current? Alternating current, as we said in the last, when we were discussing generators, is that the current gets bigger, smaller, changes direction, bigger, smaller, changes direction. Now, in South Africa, our alternating current makes 50 of these waves in 1 second. 50 hertz, 50 full vibrations every second. So that means that the current actually changes direction 100 times per second. That is a lot, and it's really important for transformers that happens, because you need to have a changing magnetic flux. The current has a constant potential difference of 220 volts. The actual potential difference, well, that's an average. It's not really constant. They call it 220, but it varies anywhere between 0 and 311, because, bear in mind, sometimes it's down there, sometimes it's up there, sometimes it's down there, sometimes it's up there. I know that looks like down there, but it's actually up there because that's a high again. It's just in the opposite direction, and up again. And so what you say is that the maximum, which is 311, is equal to, it's called the root mean square. Because of the fact that this is a sinusoidal wave, you can just square root times by the square root of 2 and you get the average. It has the same effect as 220 volts. The current also changes with changing potential difference, and the maximum current is equal to the root mean square current multiplied by the square root of 2, and the average power that is given out by an alternating current is the root mean square potential difference multiplied by the root mean square current strength. So as a dynamo moves in a magnetic field, so you are going to land up with the current going in one direction and in the other direction. You get a maximum current when the coil is moving exactly at 90 degrees to the magnetic field. Notice this side would be coming straight up, this side would be coming straight down. This side would be going horizontal. When those coils are moving at 90 degrees, at 180 degrees, in other words, in the exact same direction as the magnetic field, that's when you have zero current. And finally, when the coils are cutting again at 90 degrees is when you have maximum current. So how does the current vary? The coil's changing direction. So here's my north, my south, my north and my south, and the coil's over there. When the coil is about to go down and up, because look, it's going to be there and there, that is when you've got your maximum. You're cutting these field lines, the field lines are over there, and you are cutting them at 90 degrees. When you are in the position over here, you are moving that coil at exactly 180 degrees or 0 degrees to the magnetic field. And again, maximum over here, maximum over there, minimum in the vertical position, minimum in the vertical position. We need electric power, which is generated in power plants. Power plants produce alternating current. The current generated in the plants and generated is delivered by a connecting cable. Power loss during transmission is a big problem, and how can we minimize that? What we do is we up the potential difference as much as possible, and we lower the current as much as possible, and in that way maintain the highest level of power, because remember, power is equal to V times I. So if I make the potential difference as high as possible, I will make the current as low as possible, and therefore I will be able to maintain the power. Power is also equal to I squared R, and therefore the squaring of that current means that you will lose more power. Power plants and generators produce current with a very high EMF, and then you lower that EMF using a transformer. How do we reduce the EMF of the current? EMF, remember, is potential difference. That's your V, and therefore you use a transformer. As I've said, the current is fluctuating all the time, and your this is your maximum currents over here, and as the current is changing, so this is your current at 50 hertz, and here is, I think, the power. Yes, your power is going to change even more frequently than that, based on the change in magnetic flux, so decreasing power. And it's all got to do with I squared. So you're going to multiply, you're going to square your current every time, and that's why you're getting such a big difference in amplitude over there. The current fluctuates with time in step with the fluctuating potential difference. So here's your change in potential difference, and the maximum current is equal to the equivalent or root mean square multiplied by root 2. Power is I squared R. The maximum power is equal to twice the equivalent power because of the squaring of the current. The relationship is illustrated on the previous slide. Power is a scalar quantity, so all the values are positive. And you saw that they were all high up on the thing instead of going above and below, above and below. Now we need to look at something sort of completely different, and it's called a diode. A diode is a component that allows current to flow in one direction only. So what you get is you get forward bias diodes. So if the current is flowing from positive to negative, over here, that arrow points in that direction, and it is called forward bias, and the current is able to move through that light bulb and come back. This is called a reverse bias over here, and what happens is the following: from positive, and it jams. The arrow's pointing in that direction, which means, and there's a line there, it stops the current, blah, 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 and that circuit does not work. So that is called reverse bias, whilst when it is allowing current through, it is forward bias. We don't need to understand how diodes work any longer in the curriculum, but it's got to do with semiconductors that have got too many electrons and too few electrons, and how those electrons move from what is called the P to the N side, or from the N to the P side. And if you put it so that it goes from positive to negative, you will get a forward bias. If you put it included in the circuit with negative and positive on opposite sides, you get a reverse bias. For your purposes, you just need to know that it will follow the arrow. This thing's called a rectifier, and what rectifiers do is they allow the current to go in a certain direction. So let's take a look at what happens over here. In this diagram, I've got alternating current. So what would that oscilloscope look like? It would look like that, AC coming through. We've then got a transformer over here, primary coil, secondary coil, and that is your soft iron core in the middle. You then are going to produce alternating current over here. So at 1 second, off goes the current. It has to go in that direction, because if it attempted to go in that direction, it would get jammed. So that diode stops the current going in that direction at all. So it follows this direction and pops out the other side. What if the current is going in the other direction? Oh, sorry, I haven't finished that circuit. Goes through the load, comes along, it needs to go back to the negative somehow, and it obviously cannot go up here, because you can't have some current coming that way and some current going that way. So it can't go up in that direction. It has to come down, around, and then it is able to go back home again. So that's the one thing. Again, you would think it should be able to go through here, but then immediately it's going to get stuck because it can't go against the traffic over there. So what have we got going here? That's the direction of the traffic all the way around, and you can't have two directions. What if now the alternating current goes exactly opposite to that? So I'm going to go this way, that way, and again I'm going to go in there. If I went up, I would get blocked. If I went backwards, I would get blocked. So I have to go in this direction. Notice that as much as different things might be happening in other parts of the circuit, so in terms of the pink circuit, things are going that way, there, there, there. So in this part of the circuit, you get alternating current. Over here, it's going backwards and forwards. Here, it's going forwards only. Here, it's going forwards only. And in this part of the circuit, on the other side of the rectifier, so this is the rectifier connected on either side of the transformer solenoid, what is going to happen is just in this part of the circuit, you actually get the current always flowing in the same direction. That is direct current. So what I've done with the rectifier is I have changed alternating current into direct current. So what would this oscilloscope look like? It would look like one direction, one direction, one direction, all of the time. It would have turned all of these that are in the opposite direction to being in the same direction across that load.